Hello, it is Dr. Hakan Satiroğlu, and today I would like to go with machine learning models and interactive artifact elements I'm going to share with you to teach you. What we left, we reached some of the points earlier. PLS bots and PLS systems, and decision tree, random forest. Now we have left in our hand, in my hand, in k-nearest neighborhood and support vector machine. So I would like to make some kind of really quick neural network classification as well in order to estimate your outcome. Remember, you can have categorical or numerical outcome to predict. So this is click, one of the tutorial, in the click tutorial given, but it's a similar approach, what we are doing. Click is doing this, all of them is automatically. However, it's important to learn underneath what's going on behind this scenario. Therefore, it is important to learn these machine learning elements. I just want to share with you because this is my interested area as well. So anyway, support vector machine is this is one of the classifier that looks the best boundary with the widest margin. This is like, in algorithm is trying to find boundary that separate classes with the widest possible margin. As you can see, different two groups, and try to put the widest margin and try to create kind of like road or motorway, I must say, maybe dual carriageway, create a distance between like widest margin possible place is trying to create. So support vectors are closest points that and define that margin, and it's given. And this slide introduce this slide is introducing a little bit different. Unlike decision tree and random forest, they were classified by splitting data through a series of questions and rules. On the other hand, support vector machine classifier is like one of the approach the problem by searching for the best possible boundary between classes. So blue class and orange class, they try to create a best possible widest boundary between them. So simply, it is aim is to separate the groups between classes between each other, but to place the boundary in a way that leaves the widest possible margin is one of the core element in the main elements of that algorithm. A simple way to say this is like imagine drawing the best possible road between penguin groups. The aim is not just to draw a road that separates them, but to place the road so it is keeps the biggest safe gap from both sides. So the points nearest the road are the most influential because they decide how far the boundary can safely move without crossing into one class to or the others. I have a kind of interactive illustration for this one as well. Before jumping to the next one. Next one is going to be a nearest neighborhood. This artifact introduced support vector machine as a classifier that works very differently from trees. The explore data screen shows the penguin species from visible cluster in the feature of space, and which gives SVM something separate. So the boundary and margin screen shows the core idea SVM. As you change that regularization, because this is the introduction, it's like intro. Can you set that dash and dash lines and clear solid lines are becoming larger if you move down and up? That screen is keep changing. Also, you can change your SVM according to two different species, as you can see. So if the dash are a bit larger, then you can include more dots, and you can include more. You can hear more small detail rather than majority of outcome. You can include more participant or more penguins in your specifications in your algorithm, and you can decide you can include in your analysis. So in that sense, the SVM places a decision boundary because dash lines and between dash lines, you can include widest possible margin. And the ringed points nearest the boundary are the support vectors. So these are the support vectors because they are telling us, they're telling us all rest of the group about. So they are just, we are hearing only their voices and estimation based on their features, their widthness, depthness, whatever you are comparing. All of them, body mass, all of them are going to be measured against their flipper length, Kuhlmann depth, body mass. So you are going to check only their elements. Okay. So rest of them out of these are a bit like you are going to exclude them. So the CN kernel explorer, on the other hand, shows the linear kernel produces. Okay, let's put the linear. Linear kernel produces is more straight lines like this. If you add polynomial, you can start to see some curves in the classifications. And also, as you can see, there are more than 3 groups here included. However, on the first one, I included only 2 groups to explain SVM at the beginning. So the prediction screen, this is like, you are measuring according to, the possible probability of that specie between Adeli, Chinstrap, or Gentao. I'm not happy with this outcome here because it seems some calculation mistakes, but as soon as you change, you meant to get different results. So this is like representing only that one. It is not real case. Also, your estimation could be changed according to the different models. Please don't ignore this section now. So because algorithm is going to be set according to your codes, and algorithm is going to predict your data, your outcome according to these codes, and you need to be aware all these sections, C section and kernel, are needs to be adjusted accordingly. So the prediction screen, this is the one penguin with the given measurement. The model predicts Adeli or others. And the highest one versus the rest of the decision score is going to, because there are 2 category here, and you are going to get some one of the highest one as a best result here is, as you can see, because although I don't decide that one, this is the highest. I don't trust this one. This is the highest probability decision is if you have this kind of flipper, Kuhlmann length, and body mass combination in your measurement, then you can say 83% Adeli is that penguin. So this is your prediction. Okay. So some of the key concepts when you are making codes about this one, as you can see, some lines. You don't need to memorize them at all because currently AI is writing for us all these elements and scalars. Just I'm showing this one to give you idea about SVM. Yeah, model is run with this coding, SVC. So one is the that regularization, kernel RBF, linear polynomial or RBF. Gamma is scale auto or float, degree only or polykernel. So you can select these elements with different, but I don't suggest you to change too much in your exam or in your learning. However, in your real life, you can test which one is better, which one is best representing your data by checking accuracy or other F1 score, precision, and recall values. All that values could be checked before making decision. So now I don't need to do that one because I have a large hand, because I'm doing only representation. And I think I'm done with this support vector machine classification, and I would like to jump onto KNN. So after looking at models such as decision tree, random forest, SVM, now we come to KNN. It is a bit like similar mentality with SVM, but a bit different. Because it is looking, as you can see, between the dot, distance between the dots. SVM was putting the largest road, motorway, between the sections, and you can adjust your dash lines with making larger or smaller. However, on the other hand, KNN nearest neighbors are a bit different. it is checking only dot between the difference, distance between two dots, 2 points. The main idea is simple. When a new penguin appears, let's say, because we would like to predict, because this is new penguin, we don't have a RFID, we don't have a chip under his skin, we don't see it is special, but it is new one. And KNN looks around that penguin in the feature space and find the closest known cases. So when you try to estimate, for example, here one of the new penguin, you don't know that species blue or orange. So what we are checking, which one is the nearest? We are checking, is it nearest one? Is it nearest one? Sorry, doesn't work well. So we are checking, this is 3 centimeters, this is 2 centimeters, this is half centimeters, 0.5 centimeters. So this is the nearest one. Then we say, yeah, likely to include, this is the blue species is going to be. So but there is some parameters inside that classification. I think I should delete that one. K-neighbors classifier is these codes are working. If you don't include anything, it's going to automatically pick the all measures according to its default settings. But you can include how many of the dots is going to be included. You can simply say in your algorithm you can include how many dots is going to be checked. Okay. So then system is going to calculate some kind of probability between these lines, and highly likely what is going to be that species is going to be classified. Okay. So the final prediction is made by the majority vote. Here is if most of the nearest neighbors are Adelaide between you indicated circle, then system estimates this is Adelaide. Okay, highly likely Adelaide. If most nearby neighbors are not Adelaide, then it's not going to predict as Adelaide. It's going to predict with another species. And so this is what is happening. Okay, then let's jump back to our illustration. So this is our interactive artifact, and my HTML codes didn't work well, but I'm sure it's a bit small. But if I zoom in, just somehow it doesn't work fine. So these are the species, again, exploration with the first screen about exploration, and okay. Well, on the next one, remember we were deciding about how many neighbors we are going to check. From that circle, you can say that circle, you can say nearest neighbor. Then if you have including 13, then it's gonna including 13, and it's gonna make a void between dots, which one is the most likely. So each color here represents the species that would be predicted if a new penguin appeared in that part of the space. The boundary is not a straight line. SVM. So it means that boundary I made circle around the dot is not applicable at some point. It is checking the nearest one, then it's not going to be circle in some point. It can be maybe ellipse. It can be different to maybe triangle. But kind of you need to keep in your mind the nearest elements, nearest points is going to be checked. And it follows the local pattern nearby the points. And this is why KNN create flexible boundaries, but it can also become sensitive to noise if K is too small. Because literally, as you can see, you are checking all data, all estimation. You are get rid of. You are ignoring the rest of the data, and you are checking and you are making your estimation according to here. And yeah, this is one of the critic on the KNN. But this is a good classification algorithm, and the prediction screen. So yeah, this is I may need to give these information as well. Distance metrics. So how we generate that distance, some kind of the calculations in here. Okay, let me find distance metrics. So I'm not sure that one is too small. I'm trying to make. So between 2 point distance calculation is maybe if you have a good mathematical skills or good mathematical knowledge, you should know this one. Literally, you are taking X and Y coordination, differences and square plus them and under subsquare them, then this is the the straight edge. I don't need to explain that one, but this is the one of the technique in mathematics we are using between two dots. Then another one is the Manhattan technique. It doesn't calculate any like square or power of that differences, just taking calculation into. But I must say the first one is more precise in terms of distance. And Minkowski, I'm not sure about this one, generalized both Euclidean and Manhattan one. So literally, this is another third one. And what you need to do, yes, you are going to choose one of the technique Euclidean and flipper estimation. This is for estimation. Okay. So literally you are checking and you are making decision according to that one. And you are going to make decision. This is the decision interactive screen. If you have one penguin, a new penguin appear with 220 millimeters and flipper length, culmin length is 44, then you can agree 59 of the neighbors agree of that Gento 59% and 41% is Adeli. According to this algorithm, this mathematical calculations. So here is that prediction is a bit like vague for this species because this is the new one. Probably you need to make some more adjustment, more observation about the penguin species. And yeah, so some of the weight we can make that weight as well. This is another algorithm. You can go and check here. So distance weight, closer neighbors vote more strongly, then your calculation is going to be more relevant for the close. You are going to make more weight on the nearest neighbors. Okay? That's why distance weights and distance metric is working for. So, uniform is simply you are distributing same weight for each element between 17 neighbors. If you take distance weighted, it means you are making more weight for the nearest stuff. What is the weight is not clear here. You can highly likely you can indicate, you can define here in the codes at some point, but you need to make further research for them. Okay, so I don't need to run them in Colab, but if you really need to see whether it's working or not in the Colab, I can run separate in the separate video. But I find ending these codes and running Colab Terminator plus showing these what we did is taking time and wasting time. I think, and therefore I don't want to go for this one. So yeah, I think I'm gonna stop this training. And but I hope it was helpful for you. And thank you very much.